All right, welcome to Physics Video 6.1. We're going to learn about the basics of energy. The objectives are here on the screen. I'm not going to read through them for you, but really quickly, by the end of the video, you should understand the idea of kinetic energy. You should understand potential energy and all the different types of potential energy. The one that we're going to focus on the most this chapter is what's called gravitational potential energy. All right, so there you go. Write those down. All right, so kinetic energy. Kinetic energy is energy of a moving object. Any object that is moving has kinetic energy, which means then that if the object is not moving, it has no kinetic energy. All right, the kinetic energy that an object has depends on the velocity of the object. The faster the object is going, the more kinetic energy it's going to have. And it depends on the mass of the object. The more mass the object has, the more kinetic energy it's going to have, assuming that it's moving. Remember, no matter how massive something is, even if it's not moving, it has no kinetic energy. All right? So that's the equation for kinetic energy. 1/2 mass times velocity squared. Please be aware that it's just the velocity that is being squared. Okay? So it's actually fairly similar to momentum, right? Momentum depends on mass and velocity. Kinetic energy depends on mass and velocity. The equations are different. So there you go. All right. Probably the easiest way to do this is to do a couple examples here. So we're going to do 3 examples here on the screen. So the first one, Carl the cat has a mass of 3 kilograms, and then Dave the dog has a mass of 6 kilograms. They're going for a walk together. They both walk at 4 meters a second. So let's find their kinetic energies. All right. So here we go. For Carl, he's got a mass of 3 kilograms and a velocity of 4 meters a second. So to find his kinetic energy, I'm going to do 1/2 times his mass times his velocity squared. So you get half of 3 kilograms times 4 meters a second squared. 4 meters a second squared is 16. Half of 3 is 1.5. 1.5 times 16 gives you 24, and the units are kilogram meters squared per second squared. But since that becomes a little bit cumbersome to write, we're just going to write it as 24 joules, which is the unit that we measure energy in, joules. It's a kilogram meter squared per second squared, and joules can be abbreviated with a capital letter J. So there you go. There is Carl's kinetic energy. All right, so now we're going to do the same thing for Dave. Let's find Dave's kinetic energy. See if I can squeeze this in here. I didn't leave myself much space on this. So let's see. Dave has a mass of 6 kilograms. He's got twice as much mass, but his velocity is the same. Okay. Remember, we said more mass means more kinetic energy. Here we can calculate it and make sure that it works. So let's see. Kinetic energy is 1/2 mv squared. Half of his mass times his velocity squared. So multiply it out. 4 squared is 16 times 3 is 48 joules. Okay. So what did we get? We had twice as much mass, and we also had twice as much energy, right? Okay. So what we've just learned here is that the mass is proportional to the kinetic energy. I should say that the other way around. But so if you double the mass, you double the kinetic energy. Half the mass, half the kinetic energy, etc. All right. So in this example, Carl the cat had less kinetic energy because he had less mass. So let's move down to the next example. All right. So now Carl is jealous because Dave has twice as much kinetic energy. So to compensate, he begins running twice as fast at 8 meters a second. All right. He's figuring, well, he's got half as much energy. So to make up for it, he's going to run twice as fast. So let's see what happens. All right, so let's see. Carl still has a mass of only 3 kilograms because he's just a skinny little cat. His velocity is now 8 meters a second. He's really moving. And we're going to find his kinetic energy. So let's see what happens. Hopefully we'll have twice the velocity. We'll get twice the kinetic energy, right? So here we go. Half of the mass times the velocity squared. Let's plug in our numbers. Mass is 3 kilograms. Velocity is 8 meters a second. Don't forget to square it. So let's see, 8 squared would be 64 times 1.5 gives us 96 joules. Huh. We ended up with a lot more kinetic energy, didn't we? Look what happened. We doubled our velocity, but our kinetic energy went from 24 to 96. Our kinetic energy got multiplied by 4, which happens to be, and there's no coincidence behind this, 2 squared. Okay? Because we square the velocity, any change in velocity affects the kinetic energy twice. So if you double the velocity, the kinetic energy gets doubled twice. If you triple the kinetic energy, I'm sorry, I said that wrong. Let's do triple. If you triple the velocity, you triple your kinetic energy twice. So it would be kinetic energy times 3 times 3, or times 3 squared. Okay? So anyway, I made that more complicated than I needed to. Basically, what you need to understand is more velocity means more kinetic energy, but there's not a direct proportion. It's what's called a direct square relationship. All right. Finally, if both Carl and Dave stop moving, then neither of them have any kinetic energy. All right. All right, moving on. We can go backwards too, right? How fast would Dave the dog need to go to have a kinetic energy of 300 joules? Right? So we got to do a little bit of algebra. Ke equals 1/2 mv squared. We could just plug our numbers in and solve for v, but this is going to come up fairly often. So let's do the algebra now. We're going to multiply both sides by 2 to get rid of the 1/2. So you get 2ke equals mv squared. Trying to get v by itself, right? So we're going to divide by m. Right? And then take the square root of both sides. So you get v equals 2ke over m square root e. Okay? So let's plug in our numbers. 2 times 300 joules over 6 kilograms square root e. So 2 times 300 is 600, divided by 6 is 100, square root it, and you get 10 meters per second. All right. If you didn't write it down for some reason, there's your equation for velocity. All right. Moving along. Potential energy. Potential energy. Sorry, I just took a drink of some soda. I hope you didn't hear me swallowing there. Potential energy is energy that an object has stored or saved. Note, often potential energy can be converted into kinetic energy, and we're going to see that. In fact, a lot of times I'll say, prove to me that this object has potential energy. And the way that you'll do that is show me that that energy can be easily converted into kinetic energy. Right? So we're going to focus on 4 types of potential energy as we go through this. All right. So the first one is what I'm going to call elastic potential energy. This is energy that an elasticy object has because it's stretched or smushed. All right. If you imagine stretching a rubber band out, you're storing energy within that rubber band. If you let it go, it goes shooting across the room. Right. You're converting the elastic energy it has when it's stretched into kinetic energy it has since it's moving when you let it go. All right, and the same thing can happen to a slinky, right? If you stretch a slinky, or if you smush a spring, right? Like if you've got a spring that looks like this, and then you smush it, right? When you let go of it, it's going to go shooting up into the air. So you're starting out with elastic potential energy because it's stored since you've compressed the spring, and then when you release it, it shoots up. Now you've got kinetic energy, right? Okay. Inflated balloon is kind of like a stretched rubber band. If you let go of it, it pushes the air out and moves, so you're converting the elastic energy from the stretchiness of the balloon to the kinetic energy of motion. We haven't used the Nerf gun yet, but it's spring operated, right? So when you pull the thing back, you're compressing a spring. When you pull the trigger, it releases the spring and moves the dart forwards. All right. Regardless, in each case, if you release the object, it'll move, so the elastic potential energy is converted to kinetic energy. All right. So there we go. There is one type of potential energy. All right, the next type is electric potential energy. We can't call it EPE because that stands for elastic. So I have arbitrarily decided to call it ZPE because the Z makes me think zap, which makes me think electricity. All right, and this is energy that's stored in a battery or some sort of power source. You know, you guys have all given somebody a shock, right? That's basically electric potential energy being released. And we'll learn more about that when we do electricity later on in the trimester. All right, chemical potential energy. This is a little bit sloppy, but basically you can store energy in the chemical makeup of something, and then as you burn it, convert it to kinetic energy, right? Like gasoline, for example. You know, you're storing energy in your gasoline. When you burn it, it makes the car go. Similarly, humans store energy in food, right? You eat, you know, whatever, your Cocoa Puffs for breakfast, and then you use the calories, the energy in that food to make you move and, you know, think and do stuff. It's probably worth noting at this point that we measure energy in joules in physics, but you can actually convert from joules into calories. There's a conversion factor in the same way that, like, 1 inch is 2.54 centimeters. There is a conversion between joules and calories, which I did not look up, and I apologize, but you're sitting at a computer, so look it up. All right, there you go, chemical potential energy. Finally, this is the most important type of potential energy. This is the one that's going to occur in most of the problems that we solve. So it's called gravitational potential energy. This is energy that an object has stored because it's elevated or being held up above some lower point. A painter on a ladder has gravitational potential energy because if he takes a bad step, that gravitational potential energy becomes kinetic energy as the Earth's gravity pulls him down, right? So anything that's elevated, a skydiver, a skier at the top of a hill, a rock at the top of a cliff, any of these objects are elevated, so they've got all this gravitational potential energy. And then when you release it, the object will fall, and as it falls, it loses height, so it loses GPE, and in return, it gains kinetic energy as it goes faster and faster. All right, just like releasing a rubber band. You stretch a rubber band, let it go, it goes flying forwards. Gravity is sort of like everything being attached to the Earth by a rubber band, right? And then when you release it, the rubber band snaps it back down to the Earth. All right. Cool. Any object that's elevated automatically has gravitational potential energy. If it's at its lowest possible point, it has no gravitational potential energy. This is sort of a weird thing about gravitational potential energy, is that it depends on height. And how you measure the height sort of depends. So what we're going to do in this class is we're going to always identify the lowest possible point in the problem and call that a height of 0, and then measure up from there. All right, that way we never have a negative height. Okay? So the gravitational potential energy, which I think I said this, we're going to call GPE. I cannot make G's lately. Gravitational potential energy depends on the height, how high up off the ground it is. The higher it is, the more GPE it has. And the mass. The more mass it has, the more GPE it has. Again, assuming that it's lifted. If it's not lifted, it won't have any GPE no matter how massive it is. All right, so how do you calculate it? Kabam! There's the equation for gravitational potential energy. You take the mass, you multiply it by the acceleration of gravity. We're going to use 10 meters per second squared. We're not going to worry about the negative sign. Okay, in this class we've always made the acceleration of gravity. We're going to make it positive here. I won't go into the reasons behind it. I don't think most of you probably care. If you do care, feel free to ask me in class and I'll explain it to you. This h here represents the height of the object, how high the object is. It represents the height that the object has the potential to move down through. Okay, so let's do an example. We're back to Carl the cat and Dave the dog. This time they're sitting on a balcony watching the stars. So we're going to find their energies. Okay, so we're going to kind of go through the same process. So here we go. Carl has a mass of 3 kilograms. He's got a height of 4 meters. So to find his GPE, we're going to do M times AG times H, 3 kilograms, 10 meters per second squared, 4 meters, 3 times 10 is 30, times 4 is 120. The units we get are kilograms times meters per second squared times meters, so you get kilogram meters squared per second squared, or joules. Okay, So there's that. Do the same thing now for Dave, the dog. He has twice as much mass, same height. So let's find his GPE. So now the only difference is we've got twice as much mass. Turns out if you multiply it, it gives you twice as much GPE. Okay? So there you go. So apparently he's a jealous sort. Carl gets jealous again because Dave has twice as much GPE. So he goes up to the roof, which is 8 meters tall. So here we go. We're going to do Carl one last time. His mass is still 3 kilograms, but he goes up to a higher point. Now he's 8 meters up instead of just 4 meters up. So to find his GPE, we use the equation again. So his mass is 3 kilograms. Acceleration of gravity is 10 meters per second squared. Again, don't worry about the negative. Times 8 meters, and it gives you 240 joules. So here it turns out that the GPE is proportional to the height. Here we doubled our height and got double the GPE. Okay. Finally, notice that if both Carl and Dave are sitting on the ground, then neither of them will have any gravitational potential energy. And in the same way that we did with kinetic energy, we can work backwards with gravitational potential energy. So in this problem, we have to figure out how high the dog would have to go to have 300 joules of GPE. So here we go. His mass is 6 kilograms. His GPE is 300 joules. And we need to find the height that corresponds with that. So algebra. At this point, grab your calculator. There's a really common mistake I see students make here. All right, so we got to get h by itself. So we're going to divide by MAG. And you get this equation. All right, and plug in your numbers. The GPE is 300 joules. Mass is 6 kilograms. Acceleration of gravity is 10 meters a second squared. Okay, right now pause the video and type that into your calculator and see what you get. I am going to assume that you've now done that. So when you do this, the answer, if you figure it out, turns out to be 5 meters. All right. If you got 500 meters, then you made the mistake of typing in 300 divided by 6 times 10. But the problem is your calculator is smart and it follows order of operations. So if you did this, it just worked left to right, right? Because when you multiply and divide, you just go left to right. So it does 300 divided by 6, which is 50, times 10 is 500. That's not what we want. This is what we want. So either multiply the bottom and then divide it, or use parentheses. Or to be honest, what I always do is this. And that works too. All right. Anyway, there you go. 5 meters is your height. All right. I don't know what my time is at on the video here. There's the equation for height. Let me check out my time real quick. How are we doing? 18 minutes. Okay. All right. So finally, an object can have more than one type of energy. Example, after you drop a ball, but before it hits the ground, right? Let me go to a blank slide here. So here's our ball. Oh, here's a ball. And you drop it. Okay. When the ball gets to, for example, right here, at that moment, it's going to have gravitational potential energy because it's still up some height, and it's going to have kinetic energy because it's moving with some velocity. Okay? So it is possible for an object to have more than one type of energy. If you add those up, it gives you what's called total energy. All right? And that's going to be what we're going to start the next video with, is the idea of total energy. So other examples of things that have more than one type of energy, a flying airplane could be said to have all the types of energy, right? Flying airplane has kinetic energy because it's moving. It's got gravitational potential energy because it's, you know, way up high. It's got electric potential energy because presumably cars have batteries. I'm assuming airplanes do. It's got chemical potential energy because it runs on fuel. Elastic potential energy is a little bit of a stretch. No pun intended. Somebody in that airplane has a rubber band in her hair, all right, or his hair, all right. So there you go. Energy basics.